process. Hi, my name is Ritvik Yadav Maila, and I'll be presenting the chapter Quantitative Process Analysis, which is the seventh chapter from the book Business Fundamentals of Business Process Management. Here we go. Here's the introduction of the initial findings of chapter 7. It emphasizes on the concept of quantitative analysis and that it is a method used to evaluate and also improve business processes by using numerical data metrics and mathematical models. It helps in identifying inefficiencies, predicting outcomes, and optimizing workflows through statistical and computational techniques. Quantitative analysis plays a crucial role in understanding and improving process performance of process management. Basically, it takes all the data that we receive from certain instances and we get a assumptional outcome on what can happen for the scenario presented to us. Here is a bunch of techniques followed with quantitative analysis, which will be discussed in the further slides. One of them being flow analysis, queuing analysis, and simulations. These techniques help organizations make data driven decisions, optimize resources, and improve overall efficiency. Uh, Organizations use these techniques in their day to day lives, and modern companies more implement these techniques to get a better understanding on how to tackle financial as well as business decisions in a more efficient and leisure way. Let's first focus on flow analysis, which is one of the techniques that we'll be discussing about quantitative analysis. Flow analysis is a quantitative technique used in business process management to analyze and understand the flow of tasks, resources, and information within a process. So it is a technique that analyzes and understands how tasks influence each other and how the resources that we have present with us and the information present with us can be used to analyze the situation of a business decision or a business scenario. The goal of flow analysis is to identify inefficiencies, bottlenecks. A bottleneck is basically, imagine we come to a halt in any business decision and we'll have to tackle that situation, and there are a bunch of instances clashing each other, which is what we would call a bottleneck. And what we use flow analysis for is we use it to identify these inefficiencies, bottlenecks, and opportunities for improvement by examining how work progresses through a process. We use flow analysis to calculate the average cost of a process instance. No, just give me 1 second. Sorry about that. We use flow analysis to calculate the average costs of a process instance, knowing the cost per execution of each task, or calculate the error rate of a process given the error rate of each task. So we use flow analysis to understand how much it would cost to go ahead with a process and all the resources that get compiled in the process. Is it actually worth it to go ahead with the process, and do we actually get our bang for our buck, which is basically if by executing this process we would actually be getting back some profit. And we also get to know the error rate as well as the amount of error that could take place in case that the process goes ahead. Flow analysis allows you to calculate important process performance measures such as average cycle time. It shows how long the process takes from start to finish, process costs, error rates, and other quantitative performance indicators, which could be throughput or volumetrics. And let's get more into that in the future slides. Let us discuss some key concepts in flow analysis. One of them being cycle time calculation. Cycle time is the average time when a process starts till it completes. The chapter provides formulas for calculating cycle time in different process structures. First of them being sequential processes. So the cycle time is the sum of all the tasks cycle time, which is you take a sum, you take the mean of all the different instances that the process has been through and how much time it takes to complete each instance, and you find the mean of that and you get an average understanding of how much the cycle time is. XOR blocks, exclusive decision paths, the cycle time is weighted average of branch cycle times, and here is the formula. And we also use AND blocks, which is parallel paths, the cycle time is determined by the slowest branch within. Rework blocks, loops, the cycle time is the cycle time of the loop body divided by 1 minus r, where r is the rework probability. Ct is equal to t by 1 minus r. And another key concept is cycle time efficiency. It measures the ratio of productive time to total time, where we get to understand if the cycle time is actually efficient, and it is if the process is actually optimizing its time and using it as effectively as possible. Theoretical cycle time, TCT, divided by cycle time. Theoretical cycle time is what the process would take with no waiting time, which is an assumptional instance where everything goes perfectly smooth and time doesn't get wasted at all. And it's only the processing time. Critical path method, CPM. CPM helps identify which tasks determine the overall process duration. It involves calculating early start slash finish and late start slash finish tasks for each task, finding the critical path of tasks that have no slack, where delay impacts overall completion. So critical path method is helps us identify which tasks determine the overall process duration, focusing improvement efforts on tasks along the critical path. Little laws. The fundamental relationship connects three key process metrics. One of them being work in process, where is which is equal to lambda into cycle time, where lambda is the arrival rate. That is the amount of time it takes for the new process instances per unit time, and cycle time is CT, of course. This law is useful for what if analysis and alternate ways to calculate cycle time. Now let us get into capacity and bottlenecks, another key concept. Flow analysis helps identify bottlenecks by analyzing resource pools, set of interchangeable resources responsible for executing tasks, unit load, time that a resource pool spends on one instance of the process, unit capacity, amount of work a resource pool can deliver per time unit, theoretical capacity, maximum number of instances that can be completed per unit time, resource utilization, the arrival rate divided by theoretical capacity. We take all these uh, we take all these factors into considerance when we are trying to identify bottlenecks. The bottleneck is the resource pool within the minimum theoretical capacity, which determines the overall theoretical capacity of the process. Now let us get into another quantitative technique called queues. Queuing, the- Queuing theory is a mathematical framework for analyzing systems that experience resource contention, situations where multiple requests of or customers need service but limited resources are available to serve them. Let us take, for instance, a restaurant where there are like multiple people ordering food, but the staff is low, and people who can take their orders uh, are in a lower number, and people who can cook for them are in a lower number. But too many people are have come to the restaurant ordering for food. Basic structure of queues. At its core, a queuing system consists of a queue where items wait, one or more servers that process the items, and items, which is the instance that arrive, wait if necessary, and get processed and leave. This is a common situation in many real life worlds, as I've explained. Think of supermarkets, bank tellers, call centers, restaurants. Key queuing models. Let us focus on two fundamental queuing models, M/M/1. An MM1 queue is one of the most fundamental models in queuing theory, which is a branch of mathematics that studies It studies the behavior of waiting lines or queues. Here, M stands for Markovian, which refers to the exponential distribution of both arrival and service times. And though both of the M stands for Markovian, whereas the one stands for a single server. Whereas MMC is a fundamental queuing theory model that describes systems with multiple parallel servers processing items from a single queue. The model also assumes unlimited queue capacity, a first in first out service discipline, and that all customers who arrive will eventually be served, which is completely different when compared to MM1. A practical example of queuing would be, let us consider a customer calls support center where customer call at a rate of lambda is equal to 4, where lambda being the arrival rate, 4 calls per hour, and a single representative can handle only 5 calls per hour. This yields that the traffic intensity is equal to 4 by 5, which is 0.8, and the average customers in system is equal to 0.8 by 1 minus 0.8 is equal to 4 customers. And the average time in a system would dial down to 15 minutes. Now let us get into another technique, which is a simulation. Process simulation is a powerful analytical technique within business process management that allows organizations to model, analyze, and optimize their business processes before implementing changes in the real world. Process simulation creates a digital representation of business processes that mimics how they would behave in a real world. So we in simulation we create a virtual environment where all these hypothetical instances take place, and we gain the out we take their outcomes into consideration when and we uh, pile them all up and make a final outcome. Think of it as building a virtual laboratory where you can safely experiment with different process configurations without disrupting actual operations. Simulation tends to create a large number of hypothetical instances, and it allows you to test what if scenarios to see how process changes might impact performance, identify bottlenecks and inefficiencies that might be hidden in complex process, predict the outcomes of process improvements before investing resources, and validate proposed changes before implementation. Let us understand the anatomy of a process simulation. When a task is ready in the simulation, the simulator first looks like if there's a available resource like a worker who can do this task. If no suitable resource available, then it has to wait for some time in a queue. Once the resources are assigned, the simulator determines how long the task will take by using probability distributions, which are statistical models of how long a task would typically take, which is a general assumption. A simulator then marks the tasks as sleeping for the duration which represents the task after being worked on. After the simulator time passes, the task is marked as complete and the resource becomes available again. Importantly, the simulator doesn't actually wait real time. It uses the anatomy of a process situation doesn't actually take place in real life, as it is a very time taking process, which is why there are a lot of workarounds this process, but this is actually the normal understanding of how a process simulation takes place. This is why modern businesses can effectively simulate thousands of process instances and tens of thousands of work items in a matter of seconds, because imagine if a task took 2 hours and 2 and 20 minutes to actually take place. We would not actually wait for 2 hours and 20 minutes. We would get a general assumption, and this is where process simulation comes in handy, and where there are more faster workarounds and algorithms to go through this process quicker. Inputs of process simulation. The following are inputs and requirements that are generally used in process simulation. Processing time distributions, a statistical model that represents how long the task typically takes. This accounts for the natural variation in how long activities might take each time they are performed. Performance attributes, Additional metrics like the cost associated with performing the task and the value added by completing the task. Resource metrics. We must specify which resource pool will handle the task, the size of each resource, and the cost per time unit for each resource. These are some of the requirements for process simulation. An example of process simulation would be the Cetera insurance claim simulation. In this example, we set up and analyze a simulation for an insurance company claiming claim processing workflow under two different scenarios for operations and during a storm event that creates a spike in demand. Let me break down what this exercise is all about and what you will need to know. Cetera Insurance has a claim to resolution process that works fine under normal situations where there are roughly 9,000 calls per week. But imagine in major events like storms where call volumes or any famines that take or any floods that take place, the call volume would double to 18,000 calls per week. The process begins when customers call one of two evenly staffed call centers, each with 40 operators who verify information completeness, collect claim details, and register valid claims. All claims then funnel into a single claim handling office with 150 claim handlers, and they determine the liability, assess coverage, and process payments for approved claims. Now, let us take a recap of everything that we have covered in the previous slides. This chapter covered three quantitative process analysis techniques, three of them being flow analysis, queuing theory, and simulation, and about how quantitative process analysis actually takes place and how it uses these three techniques to get a better understanding of business instances and business scenarios. Flow analysis calculates performance measures from process models and task data, and identifies critical paths and resource utilization, and how your resources can be utilized to the best of their extent, and how time can be efficiently utilized. Higher resource utilization directly correlates with longer waiting times, which is why an optimal resource utilization must take place. Basic queuing models like MM1 calculate waiting times based on resource numbers and processing times, while queuing networks enable deeper process level analysis. Process simulation provides a versatile tool supported approach for deriving performance measures like cycle time and cost based on task resource data, where you use different instances and utilize the resources at hand to gain a better understanding of the various hypothetical assumption outcomes that can take place, and we can make a final assumption in the end. And by using these data, it making it particularly practical for comprehensive process analysis. Thank you, and this has been my presentation of the topic quantitative process analysis from chapter 7 of the book Fundamentals of Business Process Management. And this is the end of my video, and my name is Rutvik Yadav Maila. Thank you.